not recording now. It is recording. Okay, so here is the lab sheet. Hey, y'all can hear now?
Yeah.
Okay, so here we'll skip over to the second one. So they want us to use multisim. So after you all have set up multisim, you open this thing and here this entire set will be installed on your computer. So you go to this thing, NI Multisim 14.2, and then you click the thing. So that will be your loading screen. And here you'll get these three options. So since we are not using an activation code for this, we are use this thing, evaluate. Click on that. And this is your this is the very first thing you will see on the screen. So this is where you draw all your schematics. So first of all, before you even start drawing, save this entire thing, Control S. And then I already saved it here. It happens to be electricals lab one. I'll just save as sample. So this is basically the sheet you're working on. So right now, what do we need? We need a voltage source that's alternating current, a resistor, and an inductor, and this ground terminal. So to add a certain component, you could go here, place component, or else you can click Control W. So Control W, and you go here, and then here, after you select all families, you type AC source.
Yes, sir. How did you select the component?
Yeah, so you go here, place, and then
Yes.
component. Yeah, you could go and then
Okay.
select AC, and then when you type AC under all groups, you get stuff like AC current, AC power, AC voltage, and all a bunch of other stuff. So we need an AC voltage source. So we click this and press OK, and we place it somewhere around here, let's say. And then after you place it, it immediately jumps into this again. So then we again select resistor, and there is a bunch of values for this, but we are select rated. So that means we can change the resistor values to whatever we like. So select rated and place it somewhere here. And then we need one more component, and that is an inductor. Not this, not this, not this, not this. Yeah, here it
In
is. Inductor rated. That means we can change the inductor value. Double click on that and then place it here. And then close this thing for now. So this is horizontal right now, and according to the diagram, we want it vertical. So because of that, we right click and then rotate 90 degrees clockwise. Or you can use the keyboard shortcut, Control R. So this is basically it. So the next thing we'll do is, okay, we need one more component, Control W, to the ground terminal. This thing, ground, place it somewhere down here. So now we have to do all the wiring. Now according to this thing, it's just one loop and that's about it. So when you move over, I'll zoom in for you. When you move over your cursor to one of these points, it becomes a plus sign. And then you just drag and drop like this. Same for this and same for this. So that's an entire loop, and these pretty much the components as it is. So we still have to edit these values into these components. So we have to select peak to peak 10 volts, double click on this, and they say voltage peak. So what does voltage peak mean? Voltage peak means from the zero line to the top. So since we want the peak to peak to be 10, we want half of it to be 5. So from 0 to 5, it's one way, and 0 to -5, it's the other way. So here we put a 5, and the frequency, we have to set it at 7 kilohertz. So we write 7K into this. Yeah.
Get you about the peak to peak thing.
Hmm?
I didn't get you on the peak to peak thing.
Okay, so it's like this. When you have a graph, peak to peak means the highest value the voltage takes, and the lowest value the voltage takes.
So it's twice the amplitude.
Yes, it's twice the amplitude. So when we have to edit this component by double clicking it, they show us the amplitude to the peak. So sorry, the zero
Oh,
line to the peak. That is the amplitude. So we have to take half the peak to peak value in order to make it for the um, displayed value here.
I
So
get
that's 5 volts at 7 kilohertz. So since they have not given a angle for this, we put it at 0 degrees here. And then the next component. So you're clear with the voltage source, right? Parana?
Yeah, 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 yeah.
Yep. Okay, so then resistor 1. We read 100 ohms. Click on this, sorry, double click on it, and then set this to 100. Other values you don't have to bother about it. So inductor, same thing. We want 2.2 millihenries. Click on it. Set this at 2.2 millihenries and click on OK. So that's about it. So in order to measure the current and voltage, we can do something like this. We can click on place, probe, and then voltage and current. So we need drag and drop it here, somewhere here. These will, now we haven't run the simulation, so all these will be blank. But if we zoom in close enough, you will see this is the voltage, instantaneous voltage, voltage peak to peak, voltage RMS, and there's a ton of values here. So imagine that we run this thing. This is the run the simulation. Run now F5. So you press F5, close this window. So remember this says 5 volts peak, but here this says pretty much 10 volts peak. I mean, there's a tiny bit off, but then 10 volts peak. You get the point. So stop the simulation for now. So for the calculation here, they want us to record the waveform. So what do they mean? Record the waveform together with the input voltage, current waveform and the input voltage. So how do we do this? We need something
You
called an
get an
oscilloscope.
oscilloscope.
Yeah. So on this section right here, we have the multimeter. No, we don't need that. A function generator. No. Wattmeter. No. Oscilloscope. We need one of these. So we drag and drop it. So there are two terminals. We'll select the first terminal and send it right here. And this thing has to be actually a ground terminal. I select this, Control C, Control V. So then I could just get it down here. For now I'll join the second terminal also because we'll be using this terminal later. But then let's forget about it for now. Terminal 1, go straight here. So that means the difference is between this place and the ground, and we are measuring the voltage or the sine wave of this. So we double click on this. So right now it's blank, and we play it. So this is basically the sine wave, but then you can pretty much see it here. So we have to keep on reducing the waveform, the time base, until it gets somewhere here. So let's stop it for now. So this is what the waveform looks like, and we increase the scale until it fits pretty much somewhere around here. So this is a good enough view for us.
Yeah, so
Yeah.
අනිත් connections කොහෙටද යන්නේ?
So this thing
Only
is
the
called
ground and the make. Okay, make
yeah,
it correct. And big.
ground එක මෙතනයි. So anyways, yeah.
අපිට මේ මේකට ප්‍රෝටියස් පාච්ච කරන්න බෑනේ.
I mean, this would be a lot more easy and convenient for us on Proteus, but then they want us to do the experiment on Multisim. So too bad we have to do it on Multisim. Anyways, this thing is so this is the sine wave of this voltage source. So now we also want to find a way to draw the current waveform on this. But here's the trick. Um, this program does not let you use current as inside the oscilloscope. This thing only accepts voltage. So what we do, there is something called a current clamp. So what's a current clamp? So a current clamp is this right here on the right side. So we click it and we drop it right here. So what does this do? When you double click this, for every milliampere passing through this, it will output 1 volt. It converts a current into a voltage output. So what does that mean? Imagine that there is a 1 milliampere current going through this part. This probe will output a voltage of 1 volt. So if we have 2 milliamperes, it will output 2 volts. So so for now, we'll leave it at this default value and we'll click OK. And then
Yes,
we
sir.
route, yeah,
Can you talk about the thing again? The thing you put there?
sorry, this is what you call a current probe. You get it from here, current
Yeah.
clamp. So what it does is, this program does not allow you to measure current from the oscilloscope. Do you understand that part?
Yeah, yeah.
Okay, so that means we have to find a method to convert a current into a voltage so that we can read it on the oscilloscope. So do you get that part?
Hmm.
So
Yeah.
what this does is, when a certain current passes through this line right here, it will output a voltage.
Hmm.
So that means, so there is a ratio. So we define the ratio here. So imagine that there is 1 milliampere of current flowing through this line. When 1 milliampere flows across this line, it will output a voltage of 1 volt. Do you understand that part?
Yeah.
So that means imagine that we have 2 milliamperes going through here. That will output 2 volts. Get that part? It's basically a current to voltage converter.
If there's one voltage, what they give?
If there is 1 milliampere, it will output 1 volt.
Hmm.
If there is 2 milliamperes, it will output 2 volts.
Hmm. We don't change the ratio.
Now we leave it at the default stage for now.
Well, how do you run the oscilloscope?
We open the oscilloscope, press play, and this thing runs. So since we can't
Uh,
observe a proper value here, we stop it and then scroll along this line. Methana scroll by that. So this is the entire history of running the oscilloscope. To scroll it right
how
to
do you
start.
change the scale?
Scale එක වෙන වේද again. This is the time scale, that's the x-axis, and this is the y-axis. So if I increase this, make a body වෙනවා. If I decrease this, look වෙනවා.
Okay, pain.
Got it? That's all nice.
Yeah.
Anyways, we'll get to that in a while. So we have to do the wiring for the current clamp also. So we have to
Mhm.
we have to take a wire from B and then place it into the current lamp here. You can see this, right?
Mhm. Yeah.
And then since now I'll change the wire, I'll change the color of this thing to green because you'll see why. So when I play this, you get two waveforms. I play and stop it, and then you get two waveforms. Now, why I selected green is because that color will correspond to the second wave here. If you use red, you won't be able to like really identify which one is coming before and after sometimes. So, anyways, we have to adjust the scale so that it fits inside the graph. So we keep on increasing it until it gets somewhere here. Are you all following me up to that?
Yeah.
Tarana?
Yeah. Wait 1 second. I can't මට wave එකේ පොඩි අවුලක් තියෙනවා.
Split වෙන්නේ නැද්ද?
Now how do you stop it like that?
අර මේ
ගාන්න.
ස්ටොප් උඩ ස්ටොප් සයින් එකක් තියෙන්නේ. රන් එකට පස්සේ.
නෑ මතර wave එකෙන් භාගයක් පෙන්නන්නේ. ඔය වගේ full wave
ඒක
එකක්
ස්ක්‍රෝල්
පෙන්නන
ඒක
screen.
ස්ක්‍රෝල් කරන්න. අර ස්ක්‍රෝල් බාර් එකක් තියෙන්නේ. ඒක
Ah,
මුලටම
there's
scroll. Yeah. You have to
scroll.
scroll it right to the start.
Okay.
So do you see both waveforms?
Okay.
Do you see both waveforms? So set your values to 20 microseconds per division, 2 volts per division, and 20 volts per division.
හරි.
So you should get something like this ideally.
Yeah.
And then what do? We need to set a way to accurately measure the 0 points. So in that case, so when you look at this left side section of the oscilloscope, you will see these two markers. So these two markers will help you to find the 0 points. 0 points, that means where it will cross the y-axis here. So what do we do to that? So we select this point, we move it between the peak here and between the crossover point here. That means anywhere across this.
I didn't get
And
you.
then
I didn't get you.
on then මෙන්න මේ point එක මෙතන තමයි තියෙන්නේ හරිනා. There's a
Oh.
pointer here. So you move it until somewhere here. That means between the top of this red color waveform and the zero crossing point of this red color waveform. This, somewhere across this section. Otherwise, it starts glitching. I found it the hard way. So right click and then set pi value. This second option right here.
I click on the green one. No, the yellow
right
one.
click on right click on this dot. There's a dot like thing here. And then set y value. And then you set the y value to 0 and then press OK. So what that does is it sets this yellow color marker to the 0 crossing point of the red waveform and the x-axis. That's the intercept. And then you do the same for this, but we need to look at the second waveform, not the first one, not the red one. We need to look at the green one. So because of that, we right click and then we have to go down here and then click on select a trace. Click that. And so far we have been checking out channel A. That's the voltage. Now we have to check out channel B. That's the current source. That's the green path. And then click on OK. Now, and then both these points will snap onto the B path, but don't worry about that. We already set this line. We all have to work. The only thing we have to worry about is the other line. So once again, make sure that this blue pointer is between the peak of the green bit and the 0 crossing point of the green path. Right click, set y value, and then 0. So it snaps here. So do you get it up to this part?
Yeah.
Okay.
Can you explain it again? I didn't get.
Okay. So so this marker is right here. So did you get the concept of the red line and the marker?
Yeah.
So you pretty much have to do the same thing for the green line, but we have to swap where the target of the marker is. That's why we say select a trace. And then earlier this was on channel A, and then we have to swap it to channel B. That means it focuses where it looks for the crossing point on the second channel. That's the green channel. Do you get that part?
Yeah.
Yeah. And then we have to select, and then we have to do the same procedure as the first um, thingy, as in first line, set the y value to 0. So what it does is it checks along this entire green line until the next crossing point. That's this. That's right here. So that means we have one crossing point here, even if the dot is here, but there's one crossing point here, and there's another crossing point here. So we have to find the time difference between these two. Now, if you're going to count the squares, sorry, did you understand up to this point?
Yeah.
All right. So if you're going to count squares, it will take a huge amount of time. But then luckily for us, the software has solved this problem and they give a direct value of L2 minus L1. That means here, time L2 minus L1. That's in microseconds, right here.
Okay.
So what does that mean? That means the
The
time
time.
difference between this and this is 17.793 microseconds. And then here's an important step. You close this, you open this, you also double click this, send it here, and take a screenshot of this. It's Windows print screen because you are going to have to include this screenshot in your this thing report. So here, what you do is there's an equation that goes like this, this right here. So right now we have the time difference. Ne? Are you following me up to that?
Yeah.
Both of you? Tarana, Tarana, you here?
One second, I'm taking the screenshot.
All right. Yeah, make sure you save your project once in a while. You click on the background and Control S, because if you lose it, that's it. Like it's just gone.
Oh, then hari. Yeah.
Now, okay, so we need an equation to find the angle difference. So in the question, they want us to find the magnitude and the phase of the current. So we can get the magnitude of the current right here. So since they gave us the peak to peak voltage 9.99 volts, we can take it as 10 volts. We can get the current as the peak to peak current as 71.7 milliamps. And then um, we need to find the phase difference, as in the phase difference in angle. So what do we have right here? 17.793 microseconds. We have to use an equation that goes like this: angle equals frequency multiplied by time shift into 360. So right now we have the frequency, that's 7,000 or 7 kilohertz. Time shift, that's the difference between these two, 17.93 17.793 microseconds. That is 17.793 into 10 to the power of minus 6. So remember, milli is minus 3 and micro is minus 6. And then you multiply it by 360. And that means you get yourself an angle of 44.8 degrees of a phase shift. And then your current probe will tell you a magnitude of the current as 71.7 milliamperes. That's right here. So yeah, that's about it for the practical or pre-lab, the first question. So for the second question, you can just click on this, Control C, Control V, and then do the entire thing again. Wire it up. So they want us to do it in parallel, right here, in parallel with L1, and repeat the calculations carried in the first question. And then again, you run it, you stop it, scroll here, and then ekama baila natala, get down the values, and then you will also get a bunch of values here, which will be something like this: 10.276 microseconds, and you do the calculation. Magnitude is 89.6 milliamperes. It's slightly higher than this thing, which we expect, but then that's about it. So yeah, any questions? Satya?
Nah.
Tarana?
After you add the other inductor, what the
Oh,
current?
same procedure. After
It
you
was
add
high
this other,
and
the entire thing again we have to do. ඒකත් රන් කරලා මෙතන තියෙන කරන්ට් එක කියවලා මෙතන එනවා 89.6 ඒක ලිව්වා ඊට පස්සේ මෙතනත් එනවා මේක ක්ලික් කරා select a trace channel A මේක 0 කරා what the hell is going on there? නෑ නෑ ඉස්සරහම දැන් මේක වයර් කරලා ඉස්සරලා රන් කරලා ස්ටොප් කරනවා ඊට පස්සේ මෙතන මේක කියවනවා peak to peak මේ current එක ඒක ලියලා අපි යනවා මෙතනට ඔසිලොස්කෝප් එකට ඊට පස්සේ අර මාකර්ස් එක්ක දාන එක ආපෝ කරනවා මේක y value එක 0 වලට දානවා මේකත් මෙතනට ගේනවා y value එක 0 වලට කරනවා sorry ඊට පස්සේ මේකත් කියවනවා මේ දැන් 10.276 නේ ඊට පස්සේ මෙන්න මේක 10.276 කියන්නේ මෙන්න මේ පළවෙනි question එකට වඩා phase difference එක අඩුයි හැබැයි current එක වැඩි මෙතන මේ 89.6 කියලා කියන්නේ so then you have to do literally the same calculation with 10.276 right here time shift is 10.276 microseconds 7000 into 10.276 microseconds into 360 that's 25.9 degrees of a phase shift
Yeah, so
yeah
we have to make a document for the pre-lab also.
oh no
We have to bring it tomorrow.
I think yeah just bring it tomorrow
So document for the pre-lab. After the lab, we need to make a lab report also, right?
yes
After lab,
there are three parts to it there's the pre-lab the post-lab and the actual lab
for the post lab.
yeah the post-lab is pretty much this basically the report, as they say. So what we will do tomorrow is this: bring all three documents though. This is the actual lab. See, we have to. This is the yeah. This pretty much what we are doing right now, but in real life, as in the lab. See, it's the same thing, same values, same concept. So right now we are doing it in Multisim. Tomorrow we have to do it inside the lab. So that's about it. Any more questions? Anyone? Huh? Okay then. එහෙනම් කොල්ලෝ අපි ගියා.